Hey class, so what we're going to talk about today is this topic called power series. And power series are one of my favorite topics in Calculus B. And what they actually are is where we start taking the idea for an infinite series, but we start writing functions as though they're infinite series. So for example, if we take a look at this function f of x, okay, x is our input into this function. And if we look at how we're defining this, we're defining this function in terms of some infinite series where the x is showing up as being raised to some power of n. And for this case, with our power series, we're thinking of those series starting from n equals 0 now and marching all the way to infinity. So this might look a little bit bizarre, but when we actually write out all the terms of this series, just like we normally would for any infinite series, we can see exactly where that x dependence lies, where we have a term of, well, x to the 0, which would just give us a constant 1. But then we have terms like x to the first, x squared, x cubed. And of course, we're adding all these terms together. So we're really constructing this like infinitely long polynomial. And we're going to see how we can start thinking of infinite series in this way, that we could write them as though they're these infinitely long polynomial-like terms. So the other things I want to just point out in this particular example is each of these coefficients out in front of our x's are basically governed by some series function. So whatever that coefficient Cn is going to give us that particular coefficient in front of that x term. So we're really thinking about these infinitely long polynomials that we can write in this very nice infinite series form as functions. So we're going to do some examples of this today. So for example, if we make this a little more concrete, let's define a function, say g of x, where g of x we're going to write as a power series from n equals 0 to infinity. And we're writing this as 5 over n factorial times x to the power of n. So in this case, our Cn function, like we had up above, is actually 5 over n factorial. And on top of that coefficient, we're also multiplying, just like we did before, some power of x onto it. And this is how we can reconstruct that infinitely long polynomial. So for example, if we have the 0th term, again, our series is starting at n equals 0 here. This is 5 over 0 factorial times x to the 0th power. Just like we mentioned before, anything to the 0 power is 1. So if we look at the next term, so this is the n equals 0 term. If we look at the next term, the n equals 1 term, we have 5 over 1 factorial, all times x to the first. So that is our n equals 1 term. And we can keep going on further and further out, giving more terms into this infinite series, or this power series for that matter. So when n equals 2, plugging in 2 everywhere we have an n. So we have 5 over 2 factorial times x squared. And we look at the n equals 3 term next. So we have a 5 over 3 factorial times x to the 3rd power. And we could keep doing this all day, of course, but this is in general how we're thinking about these infinitely long polynomials written as these infinite series that we can start thinking of as functions themselves. So let's just clean this up a bit, okay? So this is still our function g of x, and I'm just going to do a little bit of arithmetic on those coefficients just to show you that there's really nothing funky about when we're actually doing this process. So we have that series term, n equals 0 to infinity, of 5 over n factorial times x to the power of n. And that equals 5 over 0 factorial. 0 factorial is 1. So this first term is just a 5, since x to the 0 would be 1. Next, we have 5 over 1 factorial. Well, that just gives us a coefficient of 5 again. But we do have an x, so this is 5 times x. And then we add on to the n equals 2 term. So we have 5 over 2 factorial. So this is 5 halves times x squared. And we can keep adding terms on like this. If we go to the n equals 3 term, this is 5 over 3 factorial. 3 factorial is 6. So this is 5, 6, all times x cubed. And you might be wondering, what types of things are we going to do with these power series or these infinitely long polynomial-like things? Well, interestingly enough, we're going to do operations like differentiating and integrating them. Other questions we'll ask is, if these are indeed functions, well, what values of x can we actually evaluate them at? In other words, we're going to determine what the domains are of these types of power series. As a hint, we'll see the ratio test pop up here, and we'll also define some other terms that will help us along the way, the so-called interval of convergence and radius of convergence. And then lastly, we're going to see our friend or a friendly function pop out of what we already know about geometric series, and we'll actually start being able to write functions that we know in a power series type form. So that is what's up to come.